Okay, we begin now with the formal part of the course, which starts with section 1, which I called basics. And in this section, we're going to go through some of the basic definitions in group theory, go through some simple examples to start with, and then some slightly more complex examples, which will serve as the bedrock of our examples and non-examples throughout the course. So we start with 1.1 definitions and simple examples, and there's one definition that we need before we can give our main definition of the course of the group. And that is definition 1, which is the definition of a binary operation. So a binary operation, which we'll denote by this star here, on a set, which we'll call X, is the assignment of an element of X to every ordered pair of elements of X. And so what we mean by that is we just take any pair of elements in this set X and we consider them to be different. If we say A, B, and B, A, those are going to be different elements. So I'll just write that in here. And we take each of these pairs and we assign another element of X to that pair. So we write star takes X cross X to X. So for every pair of elements in X cross X, so we take one from one copy of X and one from another copy of X, we assign another element of X. So we say then that X is closed under the operation star. So what that means is that performing the operation star doesn't make us leave the set X. So we'll take a simple example here. If I can. So an example for it then would be the integers, which we'll denote by this Z under addition. So every element, every pair of elements of Z gets assigned another element of Z under addition. So 1 plus 3 gets 4, 2 plus 5 gets 7, and so on. And 4 and 7, they're both also integers. So our set, the integers, is closed under addition. We can take a non-example here as well. And for our non-example, we could take the integers under division. Because now, for example, 2 divided by 3 is not an element of Z. Okay, so that's the binary operation, and we can move on now to our most important definition of the entire course, which of course is going to be definition 2, which is the definition of a group. So a group then is a pair G star where G is a set and star is a binary operation on G exactly as above, which satisfies the group axioms. Of which there are 3. So, the first axiom is the existence of an identity. So there is an element E in G such that for all x in G, and this upside down A, that means for all, so any possible element in G is such that x star E equals E star X equals X. So we can multiply by this identity element, which is how I'll refer to applying the operation star, and it doesn't change the element. Okay, the second group axiom is the existence of inverses. So now for all x in G, so for every possible element of the group, there exists a y in G such that xy equals yx equals E. So we have an element that cancels out every element. This E, by the way, we call the identity. Now notice I'm saying the identity, but I haven't actually said that there's only one, and will in fact go on very shortly to show that the identity is in fact unique, and these inverses that we're talking about in the second axiom are actually unique as well. But first, there's one more axiom, which is associativity. And this says that if we take any three elements in the group, then x star y star z is the same as x star y star z. Effectively, what we're saying here is we don't really need the brackets. So, right here, we don't need brackets. X star y star z is unambiguous. And in fact, this extends to multiplying together any number of elements by induction. And I'll write like this as an abbreviation for elements. Okay, so this is our definition of a group. We have this set G, this operation star, and it satisfies these three axioms. Now there's one important thing to note here. We've got three axioms, but when you're asked to check whether a set and an operation are actually a group, there's four things to check. And that's because we need to check the three group axioms but also closure, which, if you remember, was in the definition of the binary operation. Okay, let's move on now and look at some examples and non-examples. So our first example then is going to be the integers under addition, and this is a group. You can check the axioms for yourself. The identity is 0, and the inverse of an element is just minus that element. So the inverse of 2 is minus 2, and so on. So similarly, you can also see that the rationals, so the fractions under addition, and the reals under addition are groups. So number 2 is going to be the natural numbers under addition. Now this isn't a group because we don't have inverses. So if you think about what we looked at before, the additive inverse of, for example, 2 is minus 2, but minus 2 is not in the natural numbers. So the natural numbers don't have additive inverses, and therefore they can't be a group under addition. Next, we look at the rational numbers under multiplication. This seems almost like it might be a group. Indeed, it is almost a group, but there's one thing missing here. Again, this isn't a group because 0 doesn't have an inverse. And indeed, if you look, every other element does, but we require every element to have an inverse for it to be a group. So the rationals under multiplication, not a group. But if we take out 0, this is a group, and you can check all the axioms yourself. So our next example is a much smaller group. So the first 4 examples and non-examples we looked at were all infinite. This example is going to be finite, just the 2 elements plus and minus 1 under multiplication. So this is a group. So 1 is the identity. The inverse of 1 is 1. And the inverse of minus 1 is minus 1. And we can draw a multiplication table for this. Just like this, we take the multiplication there, we put 1 here, minus 1 here, 1 here, minus 1 here. And we can just write in all of the multiplication results, just like this. Our next example, again, this one is a group, is the set 0, 1, 2 under addition modulo 3, which I'll just make a note of here. So that just means we only consider the remainder when we divide by 3 at each step. So as an exercise, check this is a group and write out the multiplication table. Okay, we can have less familiar things which are groups as well. For example, let's take the set E, A, B, C. So E is going to be our identity, and A and B and C, just 3 elements. It doesn't particularly, they don't have to mean anything that we're familiar with, and we can just write out a multiplication table for this, like so. And you can check, again, this satisfies all of our axioms and closure and everything we need for this to be a group. Okay. The next example is really important because it's an example that will come up again and again, and indeed we're going to develop this example further in section 1.3. And that's the rotations and reflections of a triangle. So we can have a look at drawing a triangle here, and we can label the vertices 1, 2, and 3. And then if we think about the symmetries of this triangle, they're the rotations and reflections. So we can make a rotation by 60 degrees like this, and then we'll get the triangle with the vertices labelled like this. We can make a rotation by 120. Oh, excuse me, that's not quite right. This would be a rotation by 120 degrees. This would be a rotation by 240 degrees. And we would get 1, 3, and 2 like this. And then we've also got each one of the reflections through each of the reflective lines of symmetry, like this. So that gives us 2 rotations, 3 reflections, and the identity element where we just do nothing. So we've got the identity, 2 reflections, and 3 rotations. And this group, this set, is called D6. And we can consider this as a group because if we do any 2 of these rotations or reflections or identities, we in fact get another one of the reflections or the rotations. For example, if we do this rotation twice, we'll get this rotation. If we do a reflection and a rotation, we'll actually get another reflection, and you can check that for yourself. So this set is a group under composition, which just means we do one and then the other. Okay, a few more examples to go through here. We'll start with this one, number 9, and that's called, we're going to define a set called S1, which is the circle in the complex numbers. So it's the set of complex numbers which have modulus 1. So if I just draw the complex numbers here, and we've got the reals and the imaginaries, we've got this circle here, and that's the set S1. And in fact, S1 under multiplication is a group. Let's just have a look at that. So 1 is the identity. Now we can write any element of S1 as e to the I theta for some theta in 0 up to 2 pi. Hopefully you'll have seen that before. We're just writing it in what's called modulus argument form. And then multiplication just amounts to adding these arguments. And so using this mod arg form, closure is self-evident. And we can also then see that e to the I theta has inverse e to the minus I theta. Now associativity is always the case for multiplication in the complex numbers. If we think of how multiplication works just normally, associativity holds, and that's just what's going on here. So we've got another group here. Finally, we're going to look at 2 groups which have an important property, which is that they don't commute. So, excuse me, first we're going to look at a group of matrices called M2R. So this is the set of 2 by 2 matrices with entries in R. So entries which are real numbers. And we're going to look at M2R under addition. And sorry, excuse the slip of the tongue earlier. This does commute. So addition, as you know, A plus B equals B plus A. And that's the case for matrices as well. So this is a group. So our identity is the 0 matrix, the inverse of A, B, C, D, is minus A minus B minus C minus D. We get associativity because the real numbers under addition are associative, and we can consider each entry in the matrix separately. So associativity follows from associativity of addition in R. And closure as well. Okay, and our final example is going to be this group here, GL2R, which you probably haven't met before. It's the set of invertible 2x2 matrices with entries in R. Which is the same as the set of 2x2 matrices with entries in R and non-zero determinant. Okay, and this, as I was alluding to earlier, is not commutative. So if you've looked at matrix multiplication before, you'll know AB is not the same as B times A. But this is not necessary for a group. We still have an identity, which in this case is the identity matrix. 1 is along the diagonal and 0 is elsewhere. We have inverses by definition because we've looked at inversible matrices, which is the same as those matrices with non-zero determinant. If you haven't seen that before, don't worry. And associativity I will leave as an exercise for you to check along with closure. So you can check the details of that. The important point is that if you multiply matrices, the determinants multiply as well. So you're still going to get a non-zero determinant. Okay, so that's our examples and non-examples. We'll now just cover some very quick notation that we're going to use throughout the course. So first, we'll write x to the minus 1 for the inverse of x. We're going to write x to the n for x star x star x star and so on n times, and we'll write x to the minus n for x to the minus 1 to the power n. This notation hopefully seems familiar. It's the same you'll be familiar with from working with exponents, just over the natural numbers and the real numbers and the rationals. Okay, so now we're going to look at some basic statements in group theory and their proofs, and the techniques we're going to use here are going to be the same that you're going to use in any sort of basic proof in group theory, the way you're just looking at kind of the very basic structure of the group. Okay, so here we're going to prove, as promised, first that the identity is unique, and then that inverses are unique. Okay, so to prove the first statement, we first suppose that we have more than one identity element, E and E prime. Now we have from our group axioms that this means G star E equals E star G equals G, and G star E prime equals E prime star G equals G. And this is for all G in G. So in fact, in the first one, we'll take G to be E prime. So we get E prime, E prime star E equals E star E prime equals E prime. And in the second, we'll take G to be E. So E star E prime equals E prime star E equals E. And you can see here, we've got actually the same thing here and here. So what we end up with is E prime equals E prime star E equals E. So E prime equals E. The identity is unique. I'll write a box in general for the end of the proof. Okay, for our second statement, we take some element in the group and we suppose that both y and y prime are inverse to x. Well, then we have that x star y equals y star x equals E, and x star y prime equals y prime star x. Equals E as well. Okay, so we have y star x equals y prime star x, and then we're going to multiply on the right hand side by y, so y star x star y equals y prime star x star y, and then we know that x star y is E, and by associativity it doesn't matter which order we do the multiplications in. So on the left hand side here, we're going to get this being E, on the right hand side we're going to get this being E. So we have y equals y prime as required. Okay, we're going to now do one more proposition, which is about some basic facts about just how we work with the elements of a group. So first, if we multiply two elements together and take their inverse, it reverses the elements. Second, x to the n to the minus 1 is x to the minus n, which, if you recall, was defined as x to the minus 1 to the n. Third, x to the m, x to the n is x to the m plus n. Fourth, x to the m to the n is x to the mn. Fifth, if we have x, y equals x, z, then this implies that y equals z, so we can cancel on the left. And sixth, if we have x, y equals z, y, then this implies that x equals z, so we can cancel on the right. We're not going to prove all of these because they're very similar. So we'll prove 1 and 5 and leave the rest as an exercise. So for 1, it's a very simple matter. We just take x, y, y inverse, x inverse, y inverse, that's E. So we get x, x inverse, and then this is obviously E. So y inverse, x inverse is inverse to xy, and then by the uniqueness that we proved earlier, this means that xy inverse is y inverse, x inverse. For 5 then, we have xy equals xz, and we can multiply on both sides on the left by x inverse, and that gives us y equals z. Throughout this statement and the proofs, by the way, you'll notice I'm dropping the stars in some places, and that's going to become a thing that we do most of the time throughout. We generally will omit the star and just write together as we normally do with multiplication. Okay, and I'll just write here as an exercise, prove the rest. Okay, we have a couple more very basic definitions to do in this session, and then we'll end for today. So definition 3, G is an abelian group if for every pair of elements in G we have that x, y equals y, x. In other words, it doesn't matter which order you do the multiplication in. So our examples from earlier, and if you look back, you should hopefully be able to see that 8, 10 and 11 were non-abelian, and the rest were abelian. By the way, we also sometimes say for abelian or commutative. This is just another word that means the same thing. Okay, final definitions then. And these are just words that we'll use throughout and it'll be useful to have a name for. So the order of a group G, denoted bars G like this, is the number of elements of G. And definition 4, maybe I'll go here, the order of an element G in G, which we denote by this little o of G, is the least positive integer n, such that G to the n is the identity. If no such n exists, we say that the order of G is infinite. Don't worry too much about what that means for now. We'll come back to it and hopefully you'll be able to see what was useful, just that we define a name for it at this point. Okay, so that's all that we needed to go through in this session. So in summary, we've today seen the definition of a group. We've seen some simple examples and non-examples. We've looked at some basic proofs involving elements of groups. We've defined abelian groups, orders of groups, and orders of elements of groups. And next time, we're going to look at a specific class of examples of groups called cyclic groups.